Hello everyone, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. This is the third class on vector spaces. In this class, first we quickly recap the definition of vector space and some of the properties of vector spaces which we have discussed in the previous classes. And in this class, we discuss about subspaces, definition of subspaces, and we will show that every subspace is a vector space. And finally, we look some examples of subspaces. We have already seen the definition of vector space, but for the convenience, let us recap it again. Vector space is a non-empty set V of objects called vectors, on which two operations called vector addition and scalar multiplication are defined with some axioms, 10 axioms. Those 10 axioms are: for all u, v, w belongs to V and scalar C and D, u plus V belongs to V. This is closure property. And u plus V is equal to V plus U. This is commutative property. And u plus V plus W is equal to u plus V plus W, associative property. There is a zero vector O in V such that u plus O is equal to U. And for each vector u in V, there is a vector minus u in V called negative of u such that u plus minus u is equal to O. In group theory, these 5 axioms form an abelian group. And sixth one is the scalar multiple of u by a scalar C denoted by Cu is in V. That is, Cu belongs to V wherever C is a scalar and U is a vector in V. And C plus D times U is equal to Cu plus Du. Here C and D are scalars and U is a vector. And the ninth one is C times Du is equal to Cd times U. Finally, 1U is equal to U. If a non-empty set satisfies all these 10 conditions, we say that that set is a vector space. And minus 1U is equal to minus U. And finally, suppose Cu is equal to O for some non-zero scalar C, then U must be a zero vector O. We have seen all these properties in our previous classes. We have gone through these examples in the previous class. First one is Rn is a vector space for n greater than or equal to 1, where n is a natural number. We have proved this one in detail, from which we can conclude that any Rn, R3, R4, R10, these are all vector spaces. This is the most common model. Most of the vector spaces are similar to Rn. Later we proved signal space is a vector space which is used in signals. Similarly, we have proved space of arrows, which is used in physics, where it is related to many forces. That is also a vector space. Space of polynomials is also a vector space. Similarly, space of real valued functions will also be a vector space, where vector addition and scalar multiplication is properly defined. So these are the examples of vector spaces which we have seen in our previous classes. Now in today's class, let us discuss about the subspaces. A subspace is a vector space itself, but it is a subset to some vector space. So this is the definition. A subspace of a vector space V is a subset H of V that has three properties. First one is the zero vector of V is in H. So zero vector of V must be in H. Second one is H is closed under vector addition. H must be closed under vector addition. That means for each U and V in H, the sum, the vector addition, U plus V is in H. U plus V belongs to H. That is the second one. Now the third property, H is closed under multiplication by scalars. That is, for each U in H and each scalar C, the vector Cu belongs to H. The subset H of a vector space V satisfies these three conditions, then H is a subspace of the vector space. So for any set, if we want to prove it is a subspace, we have to check these three properties, and first of all we need to show that that set is a subset of the vector space. So in total there will be four things to be done while proving a subspace to a vector space. So every subspace will be itself is a vector space under the operations defined under V. So since H is a subset of V, the operations in V are carried to the H, then H also satisfies all the 10 conditions if those three conditions are satisfied. Note that the properties A, B, C given in the previous slide are nothing but the axioms 4, 1, 6 respectively of the definition of vector space. First property is that zero vector. A is nothing but zero vector. Zero vector is our fourth axiom. B is closed under vector addition. That is our first axiom. The next C is closed under scalar multiplication. That is the sixth axiom of the definition of vector space. So by satisfying the three conditions, H already satisfies three of the axioms of the definition of vector space. We have to look into other seven axioms, but axiom 2, 3 and 7, 8, 9, 10, these six axioms automatically true in H, since they apply to all elements of V, including those in H. There will be two types of rules or axioms. One is common to all elements. One is to be, other type are to be checked separately, individually. So these six axioms automatically true in any subset of V. Suppose if the hair of Indians is black, then for any subset in any state, we can say that the hair of the people of that state is black. So in that way, we can establish these six rules automatically true in all subsets of V. There will be another kind of rules which cannot follow automatically. Suppose Taj Mahal is in India, but we can't say Taj Mahal is in a subset, that is Telangana. Taj Mahal is in Telangana, we can't say. So those type of rules will be another four, out of which three are checked by our properties of subspace. Three are listed in the definition of subspace itself. So we have to check those three. One more is remaining, that is the fifth axiom. Fifth axiom can be proved using the three conditions. If U is in H, then by the third condition C, by scalar multiplication, -1 is a scalar, so I can multiply with -1. So -1 U is in H by property C, and we know that -1 into U is equal to -U in a vector space. So whenever U is in H, -U is also in H. So U plus -U is nothing but the zero vector. U plus -U is the zero vector. So this is our fifth axiom. So fifth axiom automatically comes from these three A, B, C definition of the subspace. So as all the axioms of a vector space are satisfied by the H, a subset of V, H itself is a vector space. H also holds all the 10 properties. So H itself is a vector space, but it is a subset of a vector space. That's why we are calling it as a subspace. So every subspace is a vector space. It follows all the axioms, it satisfies all the axioms of the vector space, and all the theory which we will prove for a vector space is true for its subspaces also. But it is a little bit easy to prove that it is a subspace, since it is enough to show that those three conditions and that particular set H is a subset of vector space V. Only 4 conditions are to be shown instead of proving all the 10 conditions. So it may be a little bit easier than proving the vector space. Let us move on to some of the examples of subspaces. And this is the first example, first and trivial example for any vector space. The set consisting of only the zero vector in a vector space V is a subspace of V, called the zero subspace and written as singleton set O. For the convenience, I am calling the zero vector as O. Since we are taking all the vectors as U, V, W, our zero vector is denoted by O. So every vector space has two trivial subspaces. V itself is a subspace to V. V is a subset of V, so V itself is a subspace of V. And for every set, for every vector space, this zero subspace, which consists of only zero element, will be there in every vector space. So let us prove the singleton element 0 also satisfies the three conditions of the subspace. First of all, in every vector space there is zero vector. So singleton set 0 is a subset of V, and zero vector 0 belongs to singleton set 0, so it contains zero vector. So we have to satisfy three conditions. Next, zero vector O plus O is again zero vector O. So there is only one vector in this set, and vector addition is closed. Similarly, if you multiply the zero vector O with any scalar C, then you will get the same zero vector O that is belongs to singleton set O for any scalar C. Therefore, all the three conditions are satisfied. Zero vector is here. It is closed under vector addition. It is closed under scalar multiplication. So we can say that Singleton set 0 satisfies all the three conditions of subspace. So singleton set 0 is a subspace of vector space. Out of the three conditions which are in the subspace, in some textbooks there will be B and C only. A follows from B and C. In fact, A follows from the B and C. But while checking, if zero vector is not there, it is unnecessary to check B and C. It is very simple to check whether zero vector is in that set or not. So for convenience, all the three conditions are listed here. So with B and C and a condition that H is non-empty, we can prove zero vector will be there. Since if H is non-empty, there must be a vector U. By condition C, we can say that minus U will be there. Since my scalar multiplication is allowed, minus 1 into U, that is minus U, will be there by condition C. U is there and minus U is there. U plus minus U is zero vector, as per one of the axiom of vector space. So since it is closed by B, zero vector must be in H. So even if you omit A, this still can be a subspace provided H is non-empty. But for convenience, it is better to check all the three conditions. Here we omitted the non-empty set condition here. It can be checked for any subset of V, a vector space. Let us go back to the one more example. We have seen that zero vector, a set containing only zero vector, is also a vector space. Since it is a subset of a vector space, it is a subspace of vector space. So a space, a subspace or a vector space can be generated by a single element also. A single element, zero element, can act as an entire space also. This is known as zero subspace. Next, let us move on to one more example. Let P be the set of all polynomials with real coefficients. P is a set of all polynomials with real coefficients with operations in P defined as functions. Then P is a subspace of the space of all real valued functions defined on R. Let D be the set of all real valued functions defined on R. Then P is a subset of D, and the relations and the two relations are defined by these two operations. Vector addition for functions f plus g is defined as f of t plus g of t for each t, and scalar multiplication cf is defined as c times f of t for each t in the domain. With these two operations, the set of all real valued functions defined on real numbers R is a vector space. Now, P is a subset of the set of all real valued functions. Let us denote this by V. Denote the vector space of all real valued functions by V. Then P is a subset of V, where V is the space of all real valued functions. Then P is a subset P contains zero polynomial, where P is equal to 0. P is the zero polynomial. So P has the zero element of the vector space V. Sum of two polynomials with real coefficient is again a polynomial with real coefficients. So it is closed under vector addition. Is closed under vector addition, and multiplication of a polynomial of real coefficients with a scalar, we get another polynomial with real coefficients. So P is also closed under scalar multiplication. So it has fulfilled all the four conditions. First, it is a subset of V. Later, the zero vector is in P. P is closed under vector addition, and P is closed under scalar multiplication. So we can conclude that P is a subspace of vector space V. So the set of all polynomials is a subspace of all real valued functions defined on real numbers. This is one more example. This is a subspace of P itself. Further, for each n greater than or equal to 0, Pn is a subspace of P. Just we have proved that P is a subspace of all real valued functions. So P itself is a vector space. Now Pn we have already seen what is Pn. Pn is a polynomial, is a set of polynomials whose degree is at most n. It contains zero element. Obviously, it is a subset of P, since P is the set of all polynomials, and Pn is the set of only of degree at most n. So Pn is a subset of P, and Pn also contains zero polynomial. We have seen in the previous class, where Pn is 0, that is a zero polynomial. That 0 also contained in Pn. So Pn contains the zero polynomial. The sum of two polynomials in Pn is also in Pn. Since if you add two polynomials of degree at most n, you can get another polynomial of degree at most n. So it is also in Pn. Similarly, if you multiply a polynomial of degree at most n with a scalar c, then you will get another polynomial with the degree at most n. So it is also in Pn. So Pn is closed under vector addition and closed under scalar multiplication. So Pn satisfies all the four conditions. First, it is a subset of P. Zero vector is there, closed under vector addition and vector multiplication. So we can say that Pn is a subspace of P. Already we have seen that P is a subspace of V, where V is the set of all real valued functions defined on R. So it will be like this. V is the set of all real valued functions. So this is a space, vector space, and in which P is a subset. It is also a vector space itself. So we call P is a subspace of V. And in this P, there is another subset, Pn, which is also a vector space itself. So it is a subspace of P, and it is a subspace of V also. But here you have to observe that the zero vector must be in the common area. So each vector space must contain this zero vector. This zero vector. So you can't get a vector space here. This vector space must contain this zero also, this zero vector also. So this is the geometrical truth representation of the three vector spaces we have seen so far. This is another example. The vector space R2 is not a subspace of R3. Already we have seen that Rn is a vector space for any n greater than or equal to 1. So R2 is a vector space, R3 is another vector space. But R2 is not a subspace of R3. Why? Let us look into this one. Since R2 is not at all a subset of R3. So R2 is different. The elements of R2 is different from elements of R3. Elements of R2 has only 2 entries. Elements of R3 has 3 entries. So these two are two different words. So one is not R2 is not a subset of R3. They will look like this. R2 is different from R3. It is not a subset of R3. So R2 is not a subspace of R3. Similarly, a plane in R3, not through the origin, is not a subspace of R3. So R3 geometrically it represents the space, 3D space. But if you take a plane in the 3D space, which is not passing through the origin, it is not a subspace of R3. Since it does not contain the zero vector. Zero vector in R3 is 0, 0, 0. That is the origin. If the plane does not passing through the origin, it does not contain this origin. So we lost that condition. So it is not a subspace. Subspace of R3. Geometrically, it will look like this. We imagine a space, and this is the plane, 3D plane. It has many 3D vectors, but it does not contain the zero vector. So it is not a vector space itself, since it does not contain zero vector. So it is not a vector space nor a subspace for R3. So this is one more example. Let H and K are subspaces of a vector space V. Then H intersection K is a subspace of V. Whenever H and K are subspaces of a vector space V, their intersection is also a subspace of V. That is what we have to prove. We know that intersection of two sets is common points of the two sets. So let us do this. Given that H and K are subspaces of vector space, whenever we are saying that these two are subspaces, these two are vector spaces themselves. So these two sets have all the 10 properties of a vector space. So zero vector must be there in a vector space. So 0 belongs to H, since H is a vector space, and 0 belongs to K, since K is a vector space. So 0, I am calling this as O, Zero vector, I am calling this as O so far. That is in both H and K. So O belongs to H intersection K. So zero vector O belongs to H intersection K. Here notice that whenever H and K are subspaces of V, H and K are subsets of V, and H intersection K is a subset of H, and H intersection K is subset of K, which are subsets of V. So H intersection K is already a subset of V. Clearly, H intersection K is a subset of V. And just now we have proved that zero vector O belongs to H intersection K. If you take two elements, U and V in H intersection K, then the vectors U and V belongs to both H and K. So they belongs to both the spaces, both the vector spaces now, since they are the subspaces of V. So UV belongs to H and UV belongs to K. So since these two are subspaces, from the closure property, first axiom, we can say that U plus V belongs to H and U plus V belongs to K. So whenever UV belongs to H intersection K, U plus V belongs to both H and K. So now I can say that U plus V belongs to H intersection K for all UV belongs to H intersection K. So H intersection K is closed under vector addition. So it is closed under vector addition. So our second property V also fulfilled by H intersection K. Now the third property, scalar multiplication. If C is any scalar and U belongs to H intersection K, then U belongs to H and U belongs to K. Since it is in the intersection, U belongs to both the sets. C is a scalar, U belongs to H implies CU belongs to H. Since H is a subspace, by sixth axiom, it is closed under scalar multiplication. So CU belongs to H. Similarly, since K is also a subspace, CU belongs to K also. U is in K also, and C is a scalar. K is a vector space. So by sixth property, sixth axiom, CU belongs to K. Now CU belongs to both H and K. So CU belongs to H intersection K. Now I can conclude that H intersection K is closed under scalar multiplication. Now all the three properties of subspace is fulfilled by H intersection K. So H intersection K is a subset of V. That is very clear. And H intersection K contained zero vector of V. H intersection K is closed under vector addition, and it is closed under scalar multiplication. So from all these, we can say that H intersection K is a subspace of V whenever H and K are subspaces of a vector space V. So let us look into one more example on subspaces. Let H and K are subspaces of a vector space V. Then H plus K is a subspace of V. H plus K is defined as it is a set of all elements W such that W is equal to U plus V for some U in H and some V in K. So W can be written as a combination of two vectors. First vector it should be from H and second vector should be from K. Whenever we can write a vector in this form, we can say that that is in H plus K. That is the definition of H plus K. So with this definition, let us prove that H plus K is a subspace of V. So this is the given hypothesis. H and K are subspaces. So H and K are obviously vector spaces also. It's the definition of H plus K is carried through here. Clearly, we can say that since V is a vector space, all these W must be in V also. Since we have closure property with respect to addition in V, U and V are nothing but the elements of V. Since they are elements of H and K respectively, again they are in V. So U plus V belongs to V by the first axiom itself. So all these W must be elements of vector space V. So clearly H plus K is a subset of V. That is clear. Now, since H and K both are vector spaces, zero vector will be there. So O belongs to H and O belongs to K. That implies zero vector O can be written as O plus O. First O is, I have taken the first O from H and the second O from K. So now O can be represented as a combination of two vectors, one from H and one from K. So now this O, zero vector, belongs to H plus K as per our definition. So zero vector O belongs to H plus K. Let us move on to the second property, closed under vector addition. Let W1 and W2 belongs to H plus K. Then each element in H plus K will be of the form U plus V, one from H and one from K. So W1 can be written as U1 plus V1 for some U1 from H and V1 from K. And W2 can be written as W2 is equal to U2 plus V2 for some U2 belongs to H and V2 belongs to K. Now W1 plus W2 is equal to W1 plus W1 is this one, U1 plus V1, and W2 is U2 plus V2, and this can be written as U1 plus U2 and V1 plus V2. Since we are in a vector space, in a vector space we have associativity and commutative property also. Using the combination of these two, we can rearrange these elements. We have both the properties. First I can exchange like this, and by associativity by commutativity I can exchange these two. Finally we will get this. So now this is from H and this is from K. U1 plus U2 belongs to H, since these two U1 belongs to H and U2 belongs to H, these two belongs to H and these two belongs to K. So first element is from UH and the second element is from K. So from our definition, W1 plus W2 belongs to H plus K, and all W1 and W2 belongs to H plus K. So therefore H plus K is closed under vector addition. Second property is also fulfilled. Now the third one, if C is any scalar and W1 belongs to H plus K, where W1 is equal to U1 plus V1 for some U1 belongs to H and V1 belongs to K, as we have seen earlier. Now CW1 is equal to C times U1 plus V1, that is CU1 plus CV1. CU1 is in H and CV1 is in K. Since these two are vector spaces by axiom number 6. So CW1 belongs to HK whenever C belongs to C is a scalar and W1 belongs to H plus K. So H plus K is closed under scalar multiplication. So H plus K satisfies all the three conditions of subspace. So we can conclude that H plus K is a subspace of V. Finally, let us prove this. That H and K are subspaces of a vector space V, and then H is a subspace of H plus K, and K is a subspace of H plus K, where H plus K is given as earlier. So now we have to prove that H is a subspace of H plus K. Earlier we have proved that H plus K is a subspace of V. Now we are going to prove that H is a subspace of H plus K. It is already given that H and K are subspaces, so they themselves are vector spaces. It is already proved that H plus K is a subspace of V. So it is enough if we will show that H is a subset of H plus K. Since H itself is a subspace and H plus K is also subspace of V. So it is enough, we will show that H is a subset of H plus K. So let U belongs to H. Let us take an element U belongs to H. If we will prove that U is in H plus K, then we can say that H is a subset of every element of H is in H plus K. So H is a subset of H plus K. So this U can be written as U plus O. So since K is a vector space, we can say that the first element is from H and second element is from K. So this is nothing but U. U is in H plus K. So I have taken an element in H that was ended in H plus K. So I can say that H is a subset of H plus K. So since these are spaces, vector spaces, and this one is a subset of this one, so we can conclude that H is a subspace of H plus K. Similarly, we can prove that K is a subspace of H plus K. If V belongs to K, then V can be written as V is equal to 0 plus V, where this 0 element O is taken from H vector space, and this is V, and this V is from K. So this V is an element of H plus K. So I have taken an element in K that is ended in H plus K. So K is also a subset of H plus K. Since both K and H plus K are subspaces, we can conclude that K is a subspace of H plus K. In this class, we have seen the definition of subspace and we have proved that every subspace is a vector space, and we have seen some of the examples for subspaces. Finally, we have proved that H intersection K and H plus K are subspaces of V whenever H and K are subspaces. Thank you for watching.